Hey guys! Okay, this is topic 6. Now for you guys, you're just going to be looking at 6.1, which is based on collision theory and rates of reaction. This is actually a good continuation from topic 5, where we talked about the energy you get from a reaction, okay, by looking at how you break bonds by investing energy, and you make bonds. If stable, you get a certain amount of energy. Now that there is a relation to that, because based on that idea, you can see how fast a reaction can be by looking at what we call chemical kinetics. Now kinetics is an energy, and that is the energy of motion. Okay? The understanding, of course, of chemical kinetics is that you're looking at speed of reaction, of how a reaction can gain speed, how it can be faster if certain parameters are met. So, which, of course, at the end of this unit, we will look at things like rate of reaction, how we can determine the rate of reaction given values. So not only is this important, it's also very useful, especially when it comes to designing experiments. So let's take a look at reaction rates. All right? When a chemical reaction takes place, so whatever chemical reaction it may be, we've looked at many chemical reactions. There are 4 things that chemists find interesting. First of all, what occurs during the reaction? Okay? What occurs during the reaction? Is there a product that's going to be formed? Is there going to be a precipitate? Is heat going to be generated? Number 2, what is the extent of the reaction? Is the reaction going to go to completion? Or the reaction actually go backwards to form what we know as equilibrium that we'll look at next time. Now, number 3 is the one that we're going to look at in this section. Does the reaction happen slowly, or does it happen very quickly? If slow, why is it slow, and can we speed it up? Because that's what society is all about lately, is how fast can I do this? Or can we do it faster? That's a good one. Number 4, what energy transfer is involved in the reaction, and could a reaction potentially occur given enough time? If you're giving 2 things, and I tell you that they're going to react, and you pour one into the other, and you don't see nothing. But if you leave it long enough, will you see something? No, that's something that scientists have been looking at for a long time. I mean, just take a look at metal. Metal reacts with oxygen. We wrote that down on paper. Copper, for example, reacts with oxygen gas to create copper oxide, right? Does this happen right in front of your eyes? Or does that take a lot of time? No. This is also something that we're going to check out, reaction rates. So, before we begin, well, let's begin. Let's actually begin by defining what is rates, or what are rates? Because there's more than just one thing that we have to take into account here. Let's take a look at this. Now, rate is defined by this expression right here, that how fast a reaction is by measuring the difference in concentration or volume, depending on what it is, per unit time. Now, that's obvious. When you look at rates, you're looking at how fast something is. And how fast something is determined by time. I hope. I have a reaction. I have a reaction right here. Okay? And let's just say A becoming B. some random reaction. Okay? As this reaction proceeds, you can see that the amount of A will decrease, while the amount of B will increase. That's something you might want to make sure you understand. Okay? And it doesn't have to be the change in concentration that you're looking at. It can be the change in volume. It can be the change of mass per unit time. Okay? Per the change of time. So it doesn't have to be concentration, but concentration is usually what people like to abbreviate with. But you know, that's one idea. Because if you look at volume, that's really the same thing. Okay, especially when you're talking about gas, that the volume of A, okay, decreases as the reaction proceeds, because the volume of B will now start to increase. When one goes down, the other goes up. Now that's pretty obvious, because as this reaction goes along, you're going to get less and less and less of this, while you're getting more and more and more and more of these. So delta C, or delta V, or delta M, whatever you're measuring, they can be monitored. Okay? So when you're doing an experiment and you're trying to figure out the rate of the reaction, other than looking at the change in concentration, you can look at the change in volume and look at the change in mass. Okay? By monitoring properties. What are some of the properties? Well, let's take a look at some example. pH is a property, right? That's pretty obvious here. pH measures the amount of hydrogen ions in a solution. I mean, hey, as the number of H plus decreases because it's turning into water, pH increases. And you will monitor the increase of pH using a pH probe. Don't tell me in a beaker you can see the decrease of H ions, man. That's crazy. What do you have, like crazy vision? You can't see the decrease of H ions, but what you can see is how pH is increasing as those acidic particle is being neutralized by basic particle. Change in conductivity. Okay, ions create a current. We all know that. They're electrolytes. When you have lots of ions in solution, it is a very good electrolyte. And therefore, it will conduct electricity very well. As you make more and more ions, obviously the conductivity will rise. So if you have a conductivity meter, or even as simple as a light bulb, you can actually see the change in conductivity based on what you see or what you measure to see, oh, you know what? You know, there's more electrolytes in here. That means you're making more ions. Now, we saw with the change in mass and volume, we're not going to talk a lot about that, because that's exactly what I used to explain this earlier. And we have a qualitative type of measurements, which is looking at the change in color. Okay, as the reaction proceeds, it gets more yellow and more yellow because the concentration of whatever chemical that makes yellow is rising. So you're looking at by color. Okay, qualitative, yes. Accuracy, also very good, especially when you're trying to come up with what we call a calibration curve. All right, so these are all things that are what we call look-fors when we're measuring the rate of something. You know, how quickly is the pH going up or going down? How quickly is it the number of electrolytes going up? Making the solutions more, I guess, rich in ions. How much of this mass is decreasing while you're looking to see that the product is increasing. Stuff like that. You know? Which brings me to a very nice example that I want you to do. So here's a reaction. This reaction involves reacting calcium carbonate. Here's your Chuck again. Seems like we can never get away from calcium carbonate. It seems like he's like our best friend. And you're reacting it with hydrochloric acid. Now, I'm sure you did this experiment before, back in, I don't know, lower grades, like grade 10, where you're mixing this calcium carbonate with hydrochloric acid and you see a fizz. And you're like, ooh, man, it's making fizzy. Yes, it's a chemical change. Now we're going to go a little bit more than that. I can tell you right now that the fizz is due to carbon dioxide being made. Because what you're going to get here is hydrogen carbonate. Hydrogen carbonate decomposes to give you carbon dioxide and water. So they're part of your products when you react the two. Right? So you're doing this experiment. You're doing this. And the volume of carbon dioxide is what you're collecting. So you're collecting this guy. So what that means is that as these two react, you're going to get more and more and more and more carbon dioxide as time goes on. Okay? This is actually a very simple experiment. Very simple experiment. Because you can actually easily determine the amount of carbon dioxide being made, okay, by, I don't know, putting together a little apparatus that collect gas. Okay? I'll show you maybe one day, just really inverting a test tube. All right, so that's what you did. Okay, actually, let me just draw what you can do. I can draw this. So here's a flask, and in this flask you have calcium carbonate and you have HCl, and they're reacting and they're making bubbles. So you just have to connect this to a tube. Okay, and for this tube, it is actually connected like this to a test tube that is inverted. Okay, and inside this test tube could be water in there. Okay, so all the gases being made are going to be used. It's going to be indicated here. So all the CO2 that you made here will come up this tube, okay, and come in and bubble up this solution and create gas. And obviously you're measuring how much gas is being made as time goes on. Okay, it's more like a little, yeah, like this. It's a little beak. There's a big beaker right here, full of liquids. Okay. Yeah. You're gonna be wondering where the liquids is coming from. Here we go. So that's the apparatus. It's pretty simple apparatus, as simple as you can get. You know, just collecting gases. So as I said, you put your calcium carbonate in here. You put your hydrochloric acid in here. You know they're going to fizz, so you're going to collect these gas through a tube and into an inverted test tube immersed in water. And apparently, okay, the gas will be collected here. And you can use a ruler to measure the amount. Okay? Because this is going to be larger and larger. Let me just illustrate that it's going to be larger. Oh my goodness, how big is that eraser? All right. Well, let's just say that's the experiment. Let's look at the data. So you're doing this experiment and you collected the data. So at time 0, obviously, you have this happening. This is time 0. Okay. So 10 seconds later, after the reaction has gone through 10 seconds, you'll notice that there's gas. Or gas. Oh my goodness, I should draw this bigger. Okay? In 20 seconds, there's more gas, and more gas, and more gas, and you're collecting the amount of gas as it moves along. Okay? Now, this is what I want you guys to do. This is something that I'm hoping you will do, and we will take this up in the beginning of class next time I see you. Is that I want you to graph this data. I want you to graph this. On the x-axis, you have the independent variable being time. Okay. On the y-axis, you have the dependent variable being volume in milliliter. I guess time you have to make sure is seconds. And when I want you to plot this, okay, see what kind of graph you're gonna make. Is there a trend? Is it a line of best fit, or is it a curve of best fit? Graph that. After graphing that, we're gonna do these. Find the average rate in 70 seconds. Then I'm gonna ask you to find the instantaneous rate at 30 seconds and the initial rate. Now you may be thinking, what's the difference between all three of these things? Oh my God, I'm freaking out. Let's just say this is what your graph looks like. Okay? Now let's say here's 70 seconds, here's 30 seconds, because that's something that you will see. Average rate. Average rate means literally average rate. Okay? From 0 seconds to 70 seconds, how fast is this reaction happening? Now, once you graph it, you can easily, determine this information by doing this. So here's your 0, that's where you started with, and here's your 70. What you're going to do between 0 and 70 is that you're going to draw a secant for this curve. Now, what is a secant? Secant is a line that cuts your curve in two places. Here's your curve. You're going to cut this curve in two places. The two places are 0 and 70. Even though this is not really 0, I'm a little off right here. Let me draw a better one. I think I can draw a better line, right? Oh my goodness, I think that one was worse. That one's just way off. And just one more time. One more time. Whatever. Okay, you're going to draw a straight line that cuts through two parts. That's a secant. In this case, you're looking at an average rate of 70. So that's why you're going from 0 to 70. So if somebody asks you, what is the average rate between, let's say, 30 and 70? So this is 30. And this is 70. And you'll draw a secant line here. Okay, what are you going to do with this secant line? Well, what else can you do? Find the slope. Slope means rate, right? As far as I'm concerned, that's what it is. It's a change in one axis over the change of another axis. That's a rate. Okay, as one increases, what happened to the other? That's a rate. So that's how you find average rate in 70 seconds. Now, how is that different than instantaneous rate? Instantaneous rate at 30 seconds. So at 30 seconds, which is right here, okay, what is the rate? Well, in this case, you're going to draw a tangent. That's a horrible tangent. Let me try again. That's worse. That looks like a secant. Okay, I get it. Here's a tangent. Okay, looks like a tangent. And you're going to find the slope of this tangent. Okay? Now, initial rate, same idea. Okay? You're also doing tangent. This tangent is the hardest tangent to draw, actually. Is the tangent that cuts through 0. Okay? It is a tangent at 0. Oh, that's beautiful, actually. Look at that. A tangent at 0. In case you don't know what a tangent is, a tangent is a line, a straight line that cuts through the curve, touching at one place, hoping at the fact that the amount here and the amount here is kind of equal. A little subjective, you think about it, especially the initial one. What I usually do is I try to move this a little far like this. Okay, if this graph goes up like this, I will try to go like that and see if I can draw my initial rate line. So the initial rate, you draw a tangent through the origin. So I want to see you guys do that for me, and then I'll take it up. Okay, and I have another one for you to do later on as as an assignment. But this is good practice. Letting you know the difference between average rate, instantaneous rate, and initial rate. And it is the initial rate that is the most important when it comes to finding the rates of reaction. Average rate, meh. Instantaneous rate, just as meh as this one. Initial rate is the most important, because the initially how fast a reaction is determined by something called rate determining step. Very important. All right, let's continue with rate equation. So a rate equation is a mathematical expression. Mathematical expression. Let's say here is my reaction, and the rate for this reaction is negative delta A over delta T. Negative is because we're seeing the number of A decreasing. Rate is not supposed to be a negative number. Heck, it can't be a negative number. How do you talk about negative rate? Unless you're talking about a vector quantity, but we're not talking about vector. These things are all scalar quantity. Okay? The amount of A is going to get lower and lower and lower. So your final concentration or final amount of A is obviously smaller than the initial amount of A, which gives you a negative number. That's why we put a negative there, so therefore it becomes a positive number. Right? So anyhow, the rate of a reaction can be determined, if this is the case, 4 ways. How much of this is decreasing against time? How much of this is decreasing against time? How much of this is making against time? So as you can see, this is a positive value, because, hey, as the reaction proceeds, you're going to get more of these than initially. Initially, you're going to get 0. Right? It's going to be 0. But as time goes on, 50 seconds, 60 seconds, 70 seconds, you're going to get a certain amount of this per time. Same with D. Okay, so in general, if this is based, of course, on variables, you can pretty much state your reaction to be any of these. That rate is equal to the negative 1x over x, okay, times the concentration, whatever this is, over time. But very rarely would you be asked to do anything like this. I mean, this is probably more popular. Okay, but coefficient, hey, don't forget about those, because coefficient is very important. Very, very important. So remember, if there are numbers here, because it's based on a balanced equation, make sure you take the reciprocal of it. Like this question right here. This is an excellent question that we're going to work through. And then we're going to call it for the day, actually. Okay, and then I'll give you some time to do that graph. So in a chemical reaction of, look, you can never get away from this reaction, calcium carbonate with hydrochloric acid, you're going to get carbon dioxide, you're going to get water, you're going to get calcium chloride. Okay? And, hey, that's going to have to balance this, or else it would make no sense, like that. But that's about it. So there's a carbon dioxide in the chemical 0.25 grams of carbon dioxide was generated in 60 seconds in a 2-liter vessel. Calculate the average rate of reaction. Okay, no problem. So the rate here is based on change in concentration of CO2 over time. Okay? Hey, what's the change in concentration? Well, you know for a fact that this reaction started with carbon dioxide being nothing. If after 60 seconds, it went up to 0.25 grams, and the vessel here is to be 2 liters, we can easily find out what the concentration is. So in this case, you're looking at 0 minus, okay, let's put that down into concentration. So 0.25. Okay, you're going to have to change that to moles, I guess, because I guess they want this in molarity per time. Okay, so that would be 0.00, sorry, 57 mole per 2 liter, which is 0.00285 molar. Okay, so 0 minus 0.002. Oh, what am I doing? I'm sorry. Final minus initial. This is the final minus 0. That was the initial. Over 60 seconds. So the rate is 0.000475 molarity per second. Okay. In terms of what how IB wants it, I think they like it like this: 0.000475 mole per liter per second. Okay, they like to do that. They don't like to use per, I guess. So that's how it is. Okay. Now, do you have to divide any of this? No, you don't have to divide anything because the quotient right here is 1. When it's 1, you can skip this pretty much. Okay. Why is this positive? Well, it's because you're looking at the amount of products being made, right? So overall, that's rate of reaction. Okay, there's nothing else that considered to be that special about this. So in the next class, we'll actually look at the collision theory. Okay, how when a reaction takes place, like for example for this one. Okay, what's really happening under a molecular level? Well, I can tell you right now that calcium carbonate and hydrochloric acid, they're gonna have to bang. Okay, they're gonna have to hit each other hard. Because if they don't, you're not gonna make these guys. Okay? Not only do you have to hit each other hard, but you have to hit each other at the right spot. Because if you don't hit the right spot, if you don't bang on the right spot, you ain't gonna get no products. So you have to bang hard, you have to bang right. And we'll see how they bang next class. All right, I'll see you guys later. Bye now.